Hello everyone, I'm Dave, and in this video course I'm going to show you how to create an alien farm game 100% from scratch using C++ and SDL2. You'll be able to place dirt, water which makes surrounding dirt wet, and different colored tiles. You'll be able to add and remove plants of different types and sizes that have shadows, move up and down, start small and grow, and can only exist on the correct types of tiles. You'll be able to add and remove animals of different types and sizes that have shadows, start small and grow, move around, and avoid overlapping plants, other animals, and certain tiles like water. We'll start by adding a simple purple checkered grid to get the basics set up. Then it will be improved by adding a tiling system that allows placement of different colored tiles. Next, an algorithm that automatically generates shadows to give a sense of depth will be added to the game. Finally, when water tiles are added or removed, the surrounding dirt tiles become wet or dry, depending on how far away they are from water. Next, plants that can be added and removed with the mouse and keyboard. Then they will be improved so that they look like they're moving up and down, and start small, then grow to their full size. Next, more plants/trees of different sizes will get added to the game, and their shadows improved to be lighter and remove overlap with other images. Finally, an algorithm will be added that checks tile types under them. That way they can only get placed on the correct ones, and if tiles are changed to types that they shouldn't exist on, they get removed. Next, animals that can be added with the mouse and keyboard that start small then grow to their full size. They will then be improved so that sometimes they either pick random points to move to or random angles to rotate to. Next, their movement will be improved further so that they avoid overlapping other animals, plants, and tile types that they shouldn't exist on, for example, water. Finally, more overlap checks will be added so that animals can no longer be placed on plants, other animals, or the wrong types of tiles. Also, an overlap check so that plants can't be placed on animals. In addition, code will be added so that the animals can be removed with the mouse, or if the tiles under them are changed to types that they shouldn't exist on. For this course, I'm going to assume that you have at least a very basic understanding of programming and game development. That way I don't have to spend forever explaining very basic concepts and can focus as much time as possible on how this specific game works. If you're not very experienced, don't worry, you should be able to follow along just fine. I've already got a small amount of code set up just to be able to do some basic things, such as load SDL2, create a window, handle mouse and keyboard input, and be able to load textures. I'm going to explain it quickly, but feel free to skip ahead if you want to. The first part is the main.cpp file. It starts by including IOStream, SDL2, and a class called game that I'll show you in a minute. Next, a Boolean variable that specifies whether the game is in full screen mode or not. Then the int main function to start the program. The seed for the random number generator is set so that it will generate different numbers every time the game is run. Try to initialize SDL and output an error message if there was a problem. Create the window either full screen or windowed mode with the title Alien Farming Game. I'll also just mention that when debugging in Visual Studio, when it hits a breakpoint, some computers lock up in full screen mode. An easy workaround for this is just to use windowed mode when debugging. A cool trick that works on some computers is that you can run it in windowed mode, but set the size of the window to the size of your screen. It will be displayed full screen, but won't lock up when debugging, and that's what I like to do. In my case, it would be switching 960 and 512 to 1920 and 1080 respectively. Next, make sure that the window was created correctly and output an error message if there was a problem. Create a renderer so that the GPU can be used to draw graphics and output an error message if there was a problem. Set the blend mode so that transparent graphics will be drawn correctly. enable anti-aliasing to make the images look better, output the name of the renderer driver to confirm that the GPU is in fact being used, get the dimensions of the window and use them to initialize the game class. Finally, make sure to clean up once the game stops running. And next, the game class, which essentially connects all the parts of the game together. It starts by including chrono to measure time for the game's clock, SDL2, and a class called texture loader and vector2d that I'll show you in a minute. It has a constructor and destructor, a few functions for processing input as well as updating and drawing everything, a variable that stores which mouse button has been pressed, define the tile size for the game, which I chose to be 64 pixels because I felt it was a good size. The constructor starts by ensuring that the window and renderer exist. Next, store the current time, start the game loop and run until it's time to stop. Determine how much time has elapsed since the last frame, store the new time for the next frame, set dt, which is the amount of time for this frame. I chose to allow it to vary based on how fast the game is running, but cap it to be no slower than 20 frames per second. I suppose it could always be fixed, but this game isn't sensitive to frame rate. Next, call the process events function, update function, and draw function. I'll be showing you all of these soon. Call the texture loader class's deallocate textures function for cleanup purposes. As I mentioned, I'll show you this class soon. For the process events function, create a variable to store whether the mouse button was pressed this frame or not. Check if the window was closed, and if so, stop running the game. Store whether the mouse button was pressed this frame or not, and which mouse button has been pressed. Check which keys have been pressed. For now, only check if the escape key was pressed, and if so, stop running the game. Get the X and Y position of the mouse, and convert from the Windows coordinate system, which is in pixels of course, to the game's coordinate system, which is what tile the mouse is in. Store all that as a vector2d, which just ends up being two floats for the X and Y position, but as I mentioned, I'll show you this class soon. Later code will be placed in this if statement that needs to be run when the mouse has been pressed, but for now it will remain empty. Similarly, the update function is empty at the moment, but code will be added here later. For now, all the draw function does is clear the window to black every frame. The texture loader class is responsible for loading and storing pointers to textures using file names. It starts by including string, unordered map, and SDL2. There's two static functions, load texture and deallocate textures. An unordered map is used to store the textures. If you're not familiar with what that is, just think of it as a type of list. It's going to be initialized in the C++ file because it's static, of course. The load texture function starts by ensuring that the file name exists. It then checks to see if the texture has already been loaded or not. If so, then it returns it. Otherwise, it sets the relative file path to the images folder and attempts to load the image by creating a new SDL surface. If everything went well, then attempt to create a texture and make sure to free the SDL surface. If the texture was created successfully, then enable transparency for it. Add it to the unordered map to keep track of it and for cleanup purposes, then return it. If for any reason there was a problem, then return null pointer instead. For the deallocate textures function, loop through the unordered map while it's not empty, get the texture at the beginning and destroy it, then erase the selected element. The vector2d class is responsible for storing the coordinates of vectors in 2D and some useful functions as well. It starts by including cmath for access to cos, sine, square root, etc. It has a few different constructors depending on how it needs to be initialized, for example with an x and y coordinate or another vector2d. There are many common functions for 2D math such as angle, magnitude, normalize, etc. Note most of the functions/constructors were implemented in the header because it's cleaner and easier to visualize. However, it's easier to implement the normalize function in the CPP file because it's a bit longer. There are also a bunch of operator overloads to make vector math intuitive and clean. Note that the x and y variables are public so that they can be easily accessed and modified without the need for get and set functions. If the game is run in windowed mode on my computer, you can see that the render is Direct3D, which of course is a common Windows API, so therefore the GPU is being used correctly. Of course, there are other valid APIs such as OpenGL, so this may be different on your machine. The window appeared is the correct size and cleared to black as it's supposed to be. If the game is run in full screen mode, you can see that the entire screen is filled with black as expected. Very nice. That's all the code that's needed to start the first lesson. However, I'm just going to quickly explain a few more classes that will be needed later. The math add-on class is responsible for adding some useful math functions. It starts by including cstdlib for access to rand for random numbers. There's a static variable for pi, 2 static functions to convert angles and radians to degrees and vice versa, 2 other static functions that output random numbers. Pi has to be initialized in the CPP file because it's static, of course. The math to convert the angles between degrees and radians is pretty straightforward. The rand float function simply casts rand to a float, then divides it by rand max. This means that it will return a random number between 0.0 and 1.0. The rand angle rad function simply calls the rand float function and multiplies it by 2 pi. This means that it will return a random number between 0.0 and 2 pi, which is the equivalent of 0 to 360 degrees, of course. The timer class is responsible for tracking how much time has passed. It has a constructor to set its maximum time as well as a default value for its current time. There are many functions that modify the current time, either by modifying it by the time step or resetting it. There are also many functions that compare the current time to other times, such as the maximum, and output a useful result. The variables that store the times have private access, so that they can only be accessed within this class. The constructor sets the values of these 2 variables. The count up and count down functions increase and decrease the current time by the time step. Note that they constrain the times to be within the range 0 to time s max. The reset functions reset the current time to the specified amount. These other functions compare the current time to the specified amount, then output whether the comparison is true or false. The compute ftime function simply outputs a factor from 0.0 to 1.0 that represents the current time divided by the maximum time. So that's all the pre-written code. I know I went through it pretty quickly since it's pretty basic. However, I just wanted to explain it because every game engine is set up a bit differently, and this way it's clear as to exactly what everything does. For the rest of the course, there will be lots of code that's unique to this particular game, so therefore I'll be spending more time going into more detail on how everything works. Lesson 1, Tiles. It's time to add a tile system to the game. By the end of this lesson, you'll be able to place dirt, water which makes surrounding dirt wet, and different colored tiles. We'll start by adding a simple purple checkered grid to get the basics set up. Then it will be improved by adding a tiling system that allows placement of different colored tiles. Next, an algorithm that automatically generates shadows to give a sense of depth will be added to the game. Finally, when water tiles are added or removed, the surrounding dirt tiles become wet or dry, depending on how far away they are from water. It's time to add a purple checkered grid to the game. I've already set up a small amount of pre-written code for the basic engine, which I explained in a previous video. It will be the starting point for this video. Let's create a class called Level that will contain all the relevant code for the purple checkered grid. Its constructor will have two inputs to set the dimensions of the level. They are measured in number of tiles along the X and Y axis. They'll have to be stored somewhere, so let's create two private variables for them. Notice that they're constant because they shouldn't need to change. Let's add the constructor in the CPP file. As you can see, it's pretty straightforward, as all it does is set the values of these two variables. A draw function will also be needed to draw the checkered grid. This means that SDL2 will also need to be included. To start, let's add two nested for loops that will loop over the entire grid. Next, set the renderer's draw color to either dark or light purple based on the XY position of the tile. It may seem a bit confusing how setting dark to X plus Y mod 2 equals 0 creates a checkered grid. Imagine a simpler case where every other column should be dark. This could be achieved by checking if X mod 2 equals 0. If Y is added to X, then it inverts the result for every other row, thus creating a checkered pattern. Now that the color's been set, let's set up a rectangle for the current tile and draw it. Its position is pretty straightforward, as it's just the X and Y coordinates multiplied by the tile size. The width and height are just tile size because that's the size of a tile. Let's create an instance of level in the game class. First, it will need to be included. Next, let's create a variable for it called level. It needs to be added to the game's constructor in the CPP file. Let's make it so that the level fills the window. Therefore, its tile count X and Y are set by dividing the window's width and height by tile size. Let's call its draw function in the game's draw function. Let's run the game and see what happens. Okay, very nice. The purple grid is being drawn correctly. It's checkered so that the dark and light colors are drawn in the correct spots. I'm going to switch the game to be full screen to see how it looks. Okay, that's weird. Why is there a black bar at the bottom? To answer this, let's look at the code in the game's constructor that sets the level's tile count X and Y. Notice that it performs integer math by dividing window width and height by tile size. Therefore, it essentially discards the remainder, meaning that the tiles will only cover the window exactly when the window is an exact multiple of tile size. Previously, the window was an exact multiple of tile size, and therefore no black bar was present. However, when full screen, my screen, which is 1920 by 1080, is an exact multiple of tile size for the width, but not the height. There are a few ways to deal with this problem. Either the code could be left as is to keep the black bar, or the code could be modified to increment the tile counts by 1 when the window's dimensions aren't exact multiples of tile size. If the black bar is really small, then the first option might be the best, but in my case it's a bit large. A third option could be to make the world far bigger than the window, and a camera system that allows scrolling could be added. However, that's a lot more complicating, and we really just need a simple solution here. Personally, I prefer to get rid of the black bar rather than keep it. To do this, let's add some additional code that checks to see if there is a remainder. If true, it will equal 1 and therefore add an additional tile to the count. If false, it will equal 0, which won't add any tiles to the count. When the game is run, you can now see that the black bar is gone. Perfect. So this means that the purple checkered grid has been added to the game correctly. It's time to improve the grid system by adding a tiling system that allows placement of different colored tiles, rather than just draw a uniform colored grid, as is done right now. The code for this could be stored in the level class. However, ultimately it will end up getting a bit long. Therefore, let's add a new class called tile to make everything more clean. To start, let's make it so that it can draw the purple checkered grid. This means that the code that currently draws it will essentially need to be copied here. Given that there will only be one tile option to start, let's leave its constructor empty for now. Let's add it to the CPP file as well. A draw function will be needed to draw the tile. Notice that it requires an X and Y position as an input. This may seem a bit strange, as usually classes for similar situations, such as units or projectiles, usually store their own position. However, in this case, the level class will store the tiles on a list, which we'll add soon, which will determine their position instead. If the position was stored here in the tile class as well, it would be overdefined and therefore ambiguous, which would be very bad. We're going to need to include SDL to remove the error where it doesn't know what the renderer is. Let's add the draw function to the CPP file as well. Let's cut the code from the levels draw function that draws the tile and paste it into the tiles draw function. As I mentioned, the tiles will need to be stored on a list in the level class, so let's add it in the header. I chose to make it a standard vector, but I suppose there are many other types of arrays that could work as well. This means that both vector and tile will need to be included. Let's create a variable called level tile size that will be equal to tile count x multiplied by tile count y. Then assign the contents of the vector to have that many elements, each initialized to an instance of the tile class. Then loop through all elements on that list and call their draw functions. Note that list tiles is an array with one dimension, which means that the x and y coordinates have to be mapped to an index, which is simply done by x plus y multiplied by tile count x. Let's run the game and see what happens. Okay, very nice. The purple checkered grid is still being drawn like it was before. This means that the code was copied over correctly and we'll now be able to add different tile types. In the tile class, let's add a new private variable called typeID that will determine what type of tile this is. Let's initialize it to be 2, which will soon end up corresponding to the purple tile. For the purposes of this game, will be considered purple grass. Let's modify the draw function to add a switch case statement that will select the correct color based on the type ID. If type ID equals 2, then the purple grass color will be selected. Notice that for now, I've also set it to be the default as well. That way, if there's an error where type ID isn't 0, 1, or 2, then purple grass will still be drawn. Similarly, let's add the dirt color. Of course, it's not the default. Finally, the watercolor. Notice that it only has one color regardless as to if it's dark or light. That way it's easier to tell the difference between water and all the other tiles. There needs to be a way to set the type ID because otherwise it would only be the default value of 2. So let's add a function for this. It will set the type ID to the input setTypeID variable. However, it will only do so if the input value is within a valid range. Back in the level class, I'm going to quickly set a few tiles to be water and a few tiles to be dirt. That way we can check if the code is working correctly or not. Let's run the game and see what happens. Okay, very nice. The first 4 tiles are being drawn as water and all have the same color. The next 4 are being drawn as brown dirt, where both the dark and light tiles are drawn correctly. This is great for a simple test, but it's not practical to set tile IDs this way. It would make the most sense to set them with a combination of the mouse and keyboard. Therefore, I'm going to remove the temporary code that modifies the tiles. Let's add 2 new functions. Set tile type ID selected and place tile type ID selected. The first will set the value of a variable called tile type ID selected that stores what type ID will need to be placed. The second will set the input tile's type ID to that value. This means that we'll have to add tile type ID selected. Let's set the default value to be 0, which is water, of course. In the CPP file, let's add the first function that sets the value of tile type ID selected, and the second function that places it. The first part determines the index based on the input x and y position. Next, ensure that it's in bounds. It's important to check both index and the x and y coordinates individually. Imagine an error where the mouse was out of bounds on the level. If, for example, x was tile count x plus 1, and y was 0, meaning that it's on the first row, but just outside the level, the first check that ensures that index is within bounds of the list would pass. The y check would pass as well, but the x check would fail. The final line set the type ID to tile type ID selected. In the game class, let's add some code in the process events function to set the level's tile type ID selected with the keyboard. If the 1, 2, or 3 key is pressed, tile type ID will be set by subtracting the key's scan code from the scan code for the first key. Next, call the level's set tile type ID selected function. For the mouse, if the left mouse button was pressed, then call the level's place tile type ID selected function to place the currently selected tile type where the mouse is located. Let's run the game and see what happens. Water should be selected by default. Okay, that's getting placed correctly. Let's press 1 and try to place some dirt. Okay, that's working correctly as well. Let's press 2 and try to place some purple grass. Okay, very nice. So that means that the grid system has been improved by adding a tiling system that allows placement of different colored tiles. It's great that the tiling system now allows placement of water, dirt, and purple grass. However, it would be nice if more colored grass tiles could be added as well. This could be done by adding additional switch case statements to the tiles draw function. However, as you can see, the code is already getting quite long. In addition, in the future, tile types are going to have more information beyond color, such as height for the algorithm that automatically generates shadows. Therefore, let's create a structure to contain all this information that will soon be added to a list. It will be called type and have 2 variables for both the dark and the light color. The list will be static and called list tile types, which means that vector will need to be included as well. Given that the list is static, it needs to be initialized in the CPP file. I've added the correct colors in order to match the switch case statement in the draw function. This means that the draw function will need to be modified quite a bit. Let's start by adding a check to ensure that type ID is within the bounds of the list. Next, let's create a variable called type selected that will reference the correct type on the list. Then replace the gigantic switch case statement with 2 lines of code. The first gets the correct color based on whether the tile should be dark or not. The second sets the renderer's draw color to that color. Notice just how much shorter the code is now. Very nice. The switch case statement was a great system for a few colors, but clearly this list system scales a lot better. Let's also modify the bounds check for the set type ID function below to be more automated by using the size of the list rather than a hard-coded value. Let's run the game and ensure that the game still works like it did before. Let's start by adding some water. Okay, good. Dirt. Okay, good. Finally, the purple grass. Okay, very nice. Everything is working correctly. Let's add a few more colors to the list. Green, yellow, blue, and white. I suppose you could even call it light gray. Of course, in the game class, let's modify the code in the process events function that sets the level's tile type ID selected with the keyboard. 4 new keys need to be added because 4 new colors were added. Let's run the game and see if the new colors work correctly or not. Let's add some rivers, some dirt with water channels, a green path. I'm going to make the land in the bottom left yellow, and for the bottom/right, let's use both blue and white. Okay, very nice. This means that the simple purple checkered grid has been improved by adding a tiling system that allows placement of different colored tiles. It's time to add an algorithm that automatically generates shadows to give a sense of depth. So how will the shadows work? While the game is a top-down 2D world, it can be thought of as having multiple layers at different heights. For example, imagine a water tile that is at a lower height than an adjacent purple grass tile. Because the purple grass tile is higher, it will cast a shadow onto the water tile. If instead the tile is dirt, it's higher up. However, it's still lower than the purple grass tile, so a shadow will be cast on it as well. Imagine a single tile that has other tiles surrounding it. If they're all purple grass, then no shadow will be cast, because they're all the same height. If the center tile is switched to water, then it's lower than the surrounding purple grass. Then the top and right edges will need a thick shadow, and the left and bottom edges will need a thin shadow. If the top and bottom tiles are also switched to water, those edges will no longer have shadows. If the left and right tiles are also switched to water, then none of the edges will have shadows anymore. However, the corners will need shadows instead. Overall, this means that the height of the top, right, bottom, and left tiles need to be checked for edge shadows. For the corner shadows, the corner tiles and the two tiles beside need to be checked. Let's start working on the code. We'll start by adding some variables in the tile class's header for the edge shadows. Let's load them in the constructor as well. This means that the renderer will be needed as an input. Of course, it will have to be added to the header as well. To load the textures, we're using the texture class, so let's include it. Given that the levels constructor calls the tiles constructor, renderer will need to be added as an input as well. The levels constructor is called in the game class, so let's add renderer as an input as well. To draw the tile shadows, let's create a new function called drawShadows in the tile class. In addition to the inputs that its draw function requires, it's going to need access to the list of tiles, as well as the tile count since they define the bounds of the level. Define a rectangle for the tile's position. Let's add some height checks for the edge shadows. Call a function that we'll be creating soon called isTileHigher that will compare the height of this tile to the top, right, bottom, and left tiles that surround it. In addition, ensure that each texture exists before drawing them. Let's add the isTileHigher function to the header. It's going to need the input position to compare to, as well as the list of tiles and tile counts. Start by ensuring that this tile's type ID is in bounds. Determine the index for the other tile based on the input X and Y position, and ensure that it's in bounds. Get the other tile's type ID, then ensure that it's in bounds, and output if the height of the other tile is greater than the height of this tile. Of course, type doesn't have a height, so that will need to be added. But before doing so, let's make sure to return false by default. Let's add a variable to the type struct called height, and update list tile types. Water will be 0, which is the lowest height. Dirt will be 1, and all the colored grass tiles will be 2. Don't forget to call the tiles drawShadow function in the levels draw function. At this point, make sure to go to your project folder and copy over the data folder if you haven't already. Then make sure there's an images folder that contains all the images for the tile shadows. There should be a total of 8, including the corners. I know we haven't added the code to draw them yet, but it's easiest to add them all at once. Let's run the game and see what happens. Okay, very nice. The shadows are now being drawn. As you can see, it's doing a very nice job with the edges, but doesn't work for the corners just yet, as expected. Let's add the variables for the corner textures to the header and constructor as well. In the drawShadows function, let's add some code to check if the top left corner needs to be drawn or not. Check to see if the corner tile, in this case top left, is higher. If so, then check the edge tiles beside the corner tile individually, and in this case, left and top tiles to ensure that they aren't higher. Finally, ensure that the texture exists and draw it if needed. Let's do the same thing, but change it slightly for the other 3 corners. Let's run the game and see what happens. As you can see, the corners look good for now for both the water and dirt tiles. In addition, notice how the dirt tiles cast shadows onto the water tiles, and the purple grass tiles cast shadows on both of them. Very nice. This means that the algorithm that automatically generates shadows has been added. While the algorithm that automatically generates shadows works quite well, the code is getting a bit long. Therefore, let's improve it by adding the shadow images to a list and switch the code to use a loop. Let's add this code in the tiles constructor. I'll temporarily leave the other textures there for now so that they can be referenced. We'll start by creating a list called list tile shadow names that will have all the names of the shadow images positions, so top left, top right, etc. Next, loop through that list, then load and add all the textures into a list we'll be creating soon called list texture tile shadows by appending the rest of the file name to it. Given that this code will be called for every tiles constructor, let's make list texture tile shadows static so that there will only be one instance of it. The individual textures are no longer needed. Given that list texture tile shadows is static, but the tiles constructor will be called lots of times, check if the list is empty before loading the textures so that they are only loaded once. Of course, the draw shadows function will need to be modified to use this list. How will it work? Well, all the code will be replaced with a for loop that loops through each element on the list one by one. Each element can be mapped to an index on a 3x3 grid, which can be used to determine the offset. The order of list texture tile shadows purposely starts with the top left, then top right, etc., which corresponds to the shown indices. Note that the center tile is skipped, but the index still increases because there is no center shadow image. Given that the indices are sorted in this order, they can be easily converted to an x and y offset. For the x offset, mod each index by 3, then subtract 1. For the y offset, divide each index by 3, then subtract 1. Let's add a for loop that loops through each of the elements on the list. It then determines the correct offset by using the count to map each element on the list to a 3x3 grid. The x and y offset are then computed using the index. Determine if the current tile is a corner or not by checking if the absolute value of both the x and y offsets are both equal to 1. If it's a corner, then perform the correct height checks and draw the shadow image if needed. Otherwise, it's an edge, so perform the correct height check and draw the shadow image if needed. I'm going to add a short comment to reflect what this code does. Let's run the game and see what happens. As you can see, the images are drawn correctly just as they were before. Very nice. This means that the code for the algorithm that automatically generates shadows has been improved. It's time to make it so that when water tiles are added or removed, the surrounding dirt tiles become wet or dry, depending on how far away they are from water. So how will this work? Well, imagine looking at it from the perspective of a water tile that's surrounded by a bunch of dirt tiles. Any dirt tiles within a specified distance, let's say 2 tiles, will need to be wet. Rather than look at it from the perspective of the water tile, we could also look at it from the perspective of a dirt tile. Let's pick this one as an example. Is there at least one water tile within the specified distance? No, so it needs to be dry. How about this one? Yes, so it needs to be wet. If another water tile is added within the specified distance of it, many other tiles will now become wet. However, the selected dirt tile doesn't change because it was already wet. Given that there can be one or more water tiles that cause a dirt tile to become wet, simply adding or removing a water tile doesn't guarantee that a dirt tile will switch from wet to dry or dry to wet. This means that anytime a water tile is added or removed, that all the dirt tiles within the specified distance of the water tile need to be checked for water. Let's add a function that when called will refresh all the tiles that surround an input position to be wet or dry depending on whether a water tile is within the specified distance or not. Let's create a variable that specifies the distance that water will travel. Next, loop through any tiles surrounding the input XY position. Ensure that the tile exists. Then define a variable that will store if water was found or not. Add another loop to check to see if at least one tile surrounding the X2, Y2 position is water. Ensure that the type ID exists. Then check if it's water by checking its name. Of course, the tile types don't have names yet, so they will need to be added soon. Finally, for the tile at position X3, Y3, set is wet to the variable found water that stores if water was found or not. Of course, is wet doesn't exist yet and will need to be added as well. So let's add it in the tile's header. It will be false by default because tiles will start off dry. Let's add name to the type struct, and therefore names to each of the tile types on the list. Currently, there's no way to make the dirt look wet. Therefore, let's modify the code in the draw function to check if this tile's type name is dirt and this tile is wet. If so, then multiply the color by a factor, fwet. 0.65 seems to work well for it. In the level class, let's call this new refresh surrounding isWet function when any tile is placed. Let's run the game and see what happens. We'll start by adding some dirt tiles. Now some water. Okay, nice. The surrounding dirt tiles are becoming wet. If the water tiles are removed, then the dirt becomes dry. Very nice. How about some larger sections? Okay, looks good. How about something a bit more realistic? A small lake and some fields where crops can be placed in the future. Perfect. This means that now when water tiles are added or removed, the surrounding dirt tiles become wet or dry depending on how far away they are from water. So now you can place water tiles. Let's make a river system that divides the world into a few islands. Let's place some dirt and make some fields where crops could be placed in the future. Of course, the water makes nearby dirt wet. Let's place some different colored tiles. How about a green path? Let's make the bottom left island yellow and the bottom right island blue and white. Overall, everything is looking good. The shadows that are automatically generated give a nice sense of depth. Very nice. This is starting to look like a farming game. This means that the tiling system is now finished. So that's the end of the free part of this course. If you enjoyed it and found it helpful, there's 2 more lessons that are paid. Lesson 2 is about adding plants, and Lesson 3 is about adding animals. They're available on Udemy. I'll put a referral link to the store page in the description below. If you buy through my referral link, I get a much larger share of the revenue. If you do end up buying the course, a review is much appreciated, but not required. Don't feel pressured to write one. So that's the end of this video, and I'll see you in the next one.